Good morning. In this video, we are going to discuss about isolectric point in amino acids. In order to understand this concept, first you should have some idea about amino acids. This is the general structure of amino acid. Even though we don't mention the position of NH2, it refers to alpha amino acid. We have beta amino acid also and gamma amino acid also. When the position is not mentioned, it refers to alpha amino acids. This is the alpha position. At the alpha position, I have NH2. It is possible to have different substituent at alpha position. Based on that, we get 20 amino acids. In our body, we have 20 natural amino acids. When we introduce some group here, we get a chiral center. The amino acids, whatever are available in nature, they are optically pure. Only L amino acid is synthesized by the nature. D amino acid is not synthesized. So all the amino acids, whatever are available in our body, they are optically pure. That's why often amino acids are taken as chiral auxiliary. We modify this and we get chiral auxiliary because it is 100% optically pure and it is cheap also, it is available in the nature. That's why we use amino acid as chiral auxiliary or modified amino acid as chiral auxiliary. Amino acid, I have NH2, which is basic. Also, I have carboxylic acid, which is acidic. If you combine one amine and carboxylic acid, they will react to give ammonium salt. Acid-base reaction will take place between them. Similarly, acid-base reaction is possible between these two. The hydrogen will be abstracted by the amine. What we get is the corresponding salt like this. The salt is neutral. The minus charge will be cancelled by plus charge, so it is considered as a neutral molecule. This structure or this ion is referred as Zeta Ion. Generally, amino acid exists in the Zeta ionic form. Consider the Zeta ion of glycine. I have taken the simplest amino acid, that is glycine. In this, there is no chiral center. This is the only amino acid without chiral center. To this, if I add H plus, O minus will take this H plus, and what we get is this one. We are adding H plus, basically we are decreasing pH. When we lower the pH, the Zeta ion can exist in this form. This is positively charged. Here it is neutral, but this is not neutral. Suppose if I increase the pH by adding a base, say we are adding sodium hydroxide and increase the pH of this medium, the base will abstract this hydrogen. In ammonium chloride, the hydrogen is slightly acidic. So the base may abstract this proton at a particular pH. After that, we may get this one. This is negatively charged. At lower pH, the Zeta ion becomes positively charged species. At higher pH, it becomes negatively charged. So there should be certain pH at which it is neutral. There should not be any positive charge or neutral charge. In other words, the pH at which it exists in the Zeta ionic form, that is nothing but isolectric point. The pH at which the amino acid is neutral. That pH is referred as isoelectric point. It is represented as P, small p and capital I. Now the question is how to predict isoelectric point. How to find out the pH at which the molecule or the amino acid will exist in the neutral form. We have seen at lower pH it will exist like this. This can undergo dissociation to give H plus and the carboxylate anion. So basically this is Zeta Ion. Say the Ka for this reaction is concentration of H plus and concentration of this Zeta Ion divided by concentration of this ion. It is weak acid, so complete dissociation will not be there. Only a small portion of this will get dissociated to give this. From this we can find out Ka. Further we can go for pKa. pKa is nothing but minus log Ka. I increase the pH of the medium. Initially the more acidic proton will undergo dissociation and we get this at certain pH. Further, this NH will undergo dissociation to give H plus and COO minus CH2 NH2. It is also possible to find out Ka and pKa for this dissociation. Ka is given as concentration of H plus and concentration of this carboxylate anion divided by the concentration of Zeta Ion. Yes, based on that we can find out Ka. Further pKa is nothing but minus log Ka. Now we have two pKa values. I represent like this pKa 1 and pKa 2. The isoelectric point is calculated based on this pKa value. If the pKa values were given directly, then this is very simple problem. Suppose if it is not given, instead of pKa value, say they are given Ka value. In that case, you have to find out pKa. pKa is nothing but minus log Ka. Isoelectric point is given by the simple formula pKa 1 plus pKa 2 divided by 2. For example, let us take the pKa value of glycine. pKa 1 value for glycine will be 2.34. pKa 2 value will be 9.60. I add these two pKa values and divide by 2. What I get is 5.97. So this is the isoelectric point for glycine. At this pH, basically this pH. At this pH, glycine will exist in the neutral form. If I lower the pH from this, the amino acid will be positively charged. You will get this. If I increase the pH, say I go to pH 7, that is neutral pH. At that pH, it will exist in this form. The lower pH, it will be positively charged. In the higher pH, it will be negatively charged. Here I have the structures of amino acids. It is important to remember at least 50% of the amino acids which we come across often. You should remember the structure of those amino acids. The first one, glycine, already we have seen. This is the simplest amino acid. There is no chiral center in this. When I introduce methyl here, the alpha position, that is alanine. When I introduce benzyl, this is phenylalanine. Basically, I have replaced one hydrogen from alanine with phenyl, so it is phenylalanine. The phenyl group, when I introduce OH at the fourth position, it is tyrosine. Instead of methyl, when I introduce isopropyl, that is valine. Butyl, it will be leucine and isoleucine. Methionine contains sulfur. When I add OH to alanine, I get serine. When I add SH, I get cysteine. To the serine itself, when I introduce methyl, we have also asparagine and glutamine. All these amino acids are neutral amino acids. There will be only one NH2 and one CO2H. We have 5 more amino acids: aspartic acid and glutamic acid. They are acidic amino acids. There will be 2 CO2H groups. Lysine, histidine and arginine, they are basic amino acids. In addition to amino acid amine, there will be one more basic nitrogen. The lysine, I have NH2. In the histidine, I have this nitrogen which is basic. Similarly, in arginine, I have this amine as well as this. Acidic amino acids are also referred as negatively charged amino acids, because at neutral pH they will carry minus charge. Basic amino acids are referred as positively charged amino acids. At neutral pH, that is at pH 7, there will be positive charge in the amino acid. Now let us consider the aspartic acid. This is the aspartic acid. At lower pH, this will be the species. Now I have 3 acidic protons. This can undergo dissociation. This OH also can undergo dissociation, and this one. The case of glycine and neutral amino acids, we have only 2 acidic hydrogens. But in acidic amino acids, that is negatively charged amino acids, we have 3 acidic protons. So for this compound, we can have pKa1, pKa2 and pKa3. In that case, how to identify the isoelectric point? Generally, students add all these 3 pKa values and they divide by 3 and they get the pKa value. That is wrong. When you have 2 carboxylic acid groups, you have to find out the pKa value of these 2 carboxylic acid groups, and you have to add them and you have to divide by 2. It's very simple. For example, for aspartic acid, pKa1 is 1.88. pKa2 is 3.65. Next one, pKa3, it is 9.6. Now I have 3 pKa values. I need not bother about this. Carboxylic acids will have pKa value below 5. This pKa value is for NH3+. Even in the case of glycine, we have seen for this proton the pKa values was around 9. For carboxylic acid OH, the pKa value will be below 5. In this case 1.88 and 3.65. So I add these two and I divide by 2. So this is how I find out the isoelectric point. What I get is 2.77. So at this pH, the molecule will be neutral. Suppose if I increase the pH to 7, I increase the pH. At higher pH, it will be negatively charged. When you lower the pH below 2.77, the amino acid will be positively charged. When you increase the pH above 2.77, it will be negatively charged. At neutral pH, it will be negatively charged. That's why aspartic acid and glutamic acid, they are referred as negatively charged amino acids. At neutral pH, that is at pH 7, they will carry negative charge. Now let us go for histidine. It is basic amino acid. It is also known as positively charged amino acid. At lower pH, say that is at pH 1, it will exist like this. In this case also, I have 3 acidic hydrogens. So there will be 3 pKa values. I give the 3 pKa values. These are the 3 pKa values for these hydrogens. I can assign this to OH. For NH3, generally it will be around 9, so 9.17 I assign for this NH3. The 6 I assign for this NH. Now, how to predict the isoelectric point? Once again, we are going to consider only 2 pKa values. I should not consider the lowest one. I have to consider these two. In the previous case, I omitted the largest value, but here I have omitted the smallest value. So I have to consider only these two, and I have to add and divide by 2. What I get is the isoelectric point. This is the isoelectric point for histidine. Generally, for neutral amino acids, the isoelectric point will be between 5 to 6. For 15 amino acids, the isoelectric point will be between 5 to 6. For acidic amino acids, aspartic acid and glutamic acid, for those two acids, the pH will be between 2 to 4. For basic amino acids, the isoelectric point will be between 7 to 10. For histidine, already we have seen, it is 7.59. For arginine, it is 10.76. For lysine, it is 9.74. There is huge difference in the pKa value of these amino acids. For example, let us consider lysine. These two are more or less same. The pKa value of this will be around 9 and this one will be around 10. There is not much difference. The case of histidine, of this will be around 6. In this case, the pKa value of this will be around 12.48. For this NH3, it will be 9. The case of histidine, here again 9.17. So this NH2 will have almost same pKa value, that is around 9. But the pKa value of this NH3 and this NH and here NH3 plus, that is different. You may know pKa value and acidity, they are inversely proportional. Higher the pKa value, less will be the acidity. I can modify this little bit. pKa and the basicity will be directly proportional. If the nitrogen is more basic, then the pKa value will be high. arginine, this NH is more basic. There will be resonance, the lone pair will fall here and this will take the proton. Because of that, this nitrogen will be more basic. That's why the pKa value is very high for this NH. When you compare these two, this is sp2 hybridized nitrogen. This one sp3 hybridized nitrogen. sp2 hybridized nitrogen are less basic compared to sp3 hybridized. That's why the pKa value is less for this NH and it is more for this.